Hi everyone, my name is William Hughes. I'm a PhD candidate at the University of Connecticut, Department of Civil and Environmental Engineering, and we also have some other students that help prepare this poster. So we have Sriram, Anna Thurman, Stephen Matil, and Indrani Chattopadhyay. And then for advisors, we also have three professors, so Wei Zhang, Nalini Ravashankar, and Ramesh Bala. So we have from the Department of Civil and Environmental Engineering and also the Department of Statistics, and we're working on the presentation today is about the clustering of bridges for vulnerability assessment from combined debris and scour. So basically the background of this is that you have some bridges, and during extreme storm events, you can also have some increased hydraulic forces, such as from the flooding or from a hurricane. And then this could cause trees upstream to fail, such as from the wind. They can fall in the river, and then they can become entrapped along bridges at their piers. This can lead to increased impact forces from these large wave debris, as well as if you get enough of these debris accumulating by the bridge piers, you can constrict that cross-sectional area of the river. This can lead to increase in the water velocity, which can then wash away the foundation of the bridge pier, and that can lead to the scour, which can then cause the structural integrity of the bridge to be threatened. And so we don't have yet good models that combine all these factors to consider the bridge risk. And so DOTs and decision makers want to have improved knowledge about these phenomena so that they can come up with better models to aid in their decision making, such as whether to close a bridge in the event of an extreme event. And so you can start with your storm and river conditions, and from that you can then predict things like the probability of a landslide, the probability of a tree upstream failing and becoming debris. And then you can estimate your scour depth and impact forces and hydraulic force in the bridge, which can then be used to evaluate the safety of the bridges. But in order to do that, we need to have a step here that we're going to focus the presentation on, which is we need to have structural models of the bridges as inputs into the fragility assessment of these bridges, the probability of these bridges fail. We need to include some structural characteristics of these bridges, but there are a lot of bridges throughout the state of Vermont, for instance, is this focus area. And so we need to come up with ways to, rather than model, say, 300 bridges throughout the state, we need to come up with ways to select certain bridges that are representative of the larger population of bridges and that optimally are representing these with a smaller number of samples, like 5, 6 structural models that represent the larger population of bridges. And so we use, in this case, clustering to come up with those optimal representative bridges. So we talked about those fragility models. So that's just models, structural models generally that predict the probability of structural damages or failures. So you can have fragility models such as, in this case, from our past research, we focused on getting the probability of landslide in the bridges and the trees falling in the river due to landslide, or also the probability of a tree failing due to wind throw, for instance. And so we want to combine this debris generation and the hydraulic forces, and also then use that to predict the probability of the bridge failing under these hydraulic events. And so we need to have those representative clusters of the structural features to come up with these ideal bridge types. So we start with we cluster them based on the key structural features. So in this case, we took the structural materials, that's steel, concrete, wood, and so forth. The type of the bridge, so is it a girder versus a culvert, things like that. And then another important characteristic of the bridges structurally is their length. So we took the total length as well as the average length of each span. And we also considered only the multi-span bridges over water because we're focusing on the scour and hydraulic risk. And the multi-span bridges will have piers, so that will be a major collector of that debris. The typical method of clustering is the k-means clustering method, and that's not suitable in this case because we have both categorical and numerical features. So for instance, structure, material, steel, and concrete, that's going to be a categorical data, whereas something like a span length is numerical. And k-means clustering cannot deal with that type of mixed data, and so we opted instead to use a more advanced k-prototypes algorithm, which can handle that mixed data types. And so we have different statistical criterion of how to select the optimal number of bridges in this number of bridge clusters in this case. And so we use different criterion such as the Elba method, the rich select criterion, and Bayesian information criterion. And these just give out some number representing like the tightness of each cluster or something along those lines, which then you can select the one with the highest or lowest value of this criterion. In this case, we went with the BIC because this is the most robust and easiest to interpret of these three criterion. And the BIC gave us 5 different clusters in this case. So you have an example here of how the clustering works. You have some new points, and then you have some idealized line dividing these different clusters into red and yellow, and then you update as you go through. You're updating and assigning, in this case, the triangles become red and yellow, and you update that sort of line dividing the clusters in this case, and then you can calculate your centroid of each cluster, the center of each cluster, and then that would serve as your most representative point from that class. So we have different breakdown of the different clusters in this case. So we see we have one type that is 20% of bridges about, it's concrete. And so that's identifying most of the concrete bridges, and you have 80% that are steel. And within those 80% steel, they break down further. So there's much more variety in the steel bridges compared to the concrete bridges are typically sort of short culverts. So those are all grouped together because there's not much variability. Concrete's much more homogeneous compared to steel. But because that variability, steel has different clusters within it. So you have different based on per meter span length. So maybe this one is the average span length is 50 meters versus 90 versus a couple of longer ones of 140 or even almost 300. And so you can see the variation of the different clusters throughout the state. So they're kind of spread out everywhere, but you have these different assignments of each bridge. So this bridge might be a long steel or a short steel or a concrete. So we can assign these representative bridge types to it in order to reduce the number of structural models. And you can see this in this table. So for each of these 5 clusters, we have the most representative bridge, which is given by the bridge ID, and then its span length and its total span length and average span length. And so you can then model these most representative bridges of each of these clusters. Then we model 5 bridges instead of the 300 plus that we had started with in the state of Vermont. And so to summarize and conclude, we have gained some important insight from this clustering into the characteristics of the Vermont bridges. So we saw a breakdown of the steel versus concrete. We saw the similarities between concrete compared to the variation in the steel. It requires a couple more representing models. And we were able to pick out these. In this case, we chose 5 bridges that are most representative, and then we can continue forward with that by including the debris and scour in these structural models now, and then we can predict the probability of failure under these different storm or hydraulic conditions. And then the ultimate goal would be to develop from these fragility models a tool or user interface or lookup table that decision makers and DOTs can use to quickly forecast for a given upcoming storm the probability or risk of failure of this bridge, and then use that to decide whether this bridge is safe for operation or whether it should be closed, and that would aid in helping to save many, many lives in the event of an upcoming storm. And so we just want to acknowledge our TIDC and the TOT technical champions that would help with this project, and all our freshman students who also helped out. And thank you for watching this presentation. Have a good day.